All right, let's take those same vectors, 0, 1, 0. And this is a type of multiplication of two vectors. We have already seen a type of vector multiplication, that was the scalar multiplication, but that only involved one vector, right? Alpha times b involves the scalar alpha, and then it has the vector b. That's just a scalar multiplication. But now we have two vectors and we want to multiply together. And then the one we're eventually going to get to, well, is the most involved one, is the cross product, which is also a multiplication of two vectors. And just so you know, I mean, given two vectors, you can say, how can I multiply them? There's actually many ways to do that, and there's more than what's here. I mean, there's something called a Hadamard product that's often really useful in computer science and programming. These are the ones that we need, and they're most common because they have really neat physical applications and most useful. The dot product, we actually have seen just a glimpse of it in the beginning, chapter 1 of book 3, and it's a very useful way to multiply vectors. And it's very simple too. It's actually compute the dot product of u dot v. It's a multiplication of two vectors. So as input, you take two vectors. And its output, though, is a scalar. And then we'll talk about what that scalar means, the interpretation of that scalar. That's as opposed to over here, where the input of a cross product is two vectors, and the output is another vector. So yeah, these two ways of multiplying vectors are very different, and they have very different interpretations of meanings. Okay, u dot v, what you're going to do is you're going to take, it's very similar to the magnitude or length calculation we just did. You're going to take this times this, plus this times this, plus this times this. So it's got this component-wise aspect, but then you're going to add things together. So I'm going to do, I guess the definition, if this is u1, u2, u3 are the three components of these R3 vectors. And this one would be v1, v2, v3. In general, the definition is u1, v1 plus u2, v2 plus u3, v3. And I could have n-dimensional vectors, and so I just say plus dot, 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 up to un, vn, right? So I can do this I can dot product vectors of any dimension. That's different though for the cross product. I can only do cross product for R3 vectors, right? I have to input two R3 vectors, and it'll output an R3 vector. Here I can do this for any n. Makes it very extensible. So for us then, u dot v for this particular example is just 0 times 1, 1 times 2, 0 times 3, add all those together, so we get a 2. And this is related to, so the dot product has some really gives useful information in the following sense. You're going to see a couple activities that will help you visualize this. But if I have two different vectors and I dot them, if I get a number of 0, it's going to mean they're perpendicular or orthogonal. We don't say perpendicular when we get to higher dimensional space like Rn space, we start saying orthogonal. If they have a very big positive number, and what's very big, we'll talk about that in a moment, but if they have a very big positive number, it means they point mostly in the same direction. If they have a big negative number, it means they point mostly in the opposite direction. Again, you're going to see some applications that'll help you in activities in chapter 1 that'll help you understand those main principles of the dot product. So again, the dot product tells us how much two vectors are pointing in the same perpendicular or opposite directions. And why is that the case? Well, also from chapter 1 of book 3, we have this property about the angle between two vectors. So we had this formula, we saw this briefly in the beginning of book 3, and I just want to point out again. We have a box here. When we first learned about vectors, we saw this also in book 3 and it's repeated here. This is if you have two R3 vectors, the angle between them, and is given this by this formula, and if they become Rn vectors in general, you can just say this dot product formula here. So theta is the arc cosine of this, or you often see this formula written this way. The cosine of theta is that, or theta is the arc cosine of u dot v over the magnitude of u, the magnitude of v. So you're going to normalize this dot product. And that'll tell you is too big for this. So are they pointing mostly to a really big value between those? Are they pointing mostly in the same direction? Or is it kind of smaller and closer to 0 and they'd be pointing maybe almost perpendicular? And by normalizing, we take care of that. We'll actually get an angle between these. So again, u dot v gives you a general sense of how much they point in the same direction, but you can find out exactly how much they point in the same direction by getting the precise angle. Okay, so next comment on dot products. Easy to compute them, you're going to practice doing that, and easy to visualize. I want to talk about a few of the applications. Okay, so then there's a 2-page spread here. Personality maps and search engines, and these are activity pages in our graph paper, so you'll have a choice of doing some of these. I definitely recommend either one of these or both. They'll give you really neat ideas on how dot products are used in everyday applications. So one of the ones that got me super excited in taking a path towards the research that I've done in search engines and how Google works and the science behind ranking was a one page in one of my favorite science books by my mentor, Carl Meyer, Matrix Analysis of Applied Linear Algebra. He talks about how search engines, these were the early search engines, and there's still parts of Google and major search engines that use this, but certainly smaller contained search engines like a library search engine or a business intranet search engine. Think of documents as vectors in space. Of course, they'd be in the English language has about 400,000 words in it, so they'd be vectors in very big N, and it's about 400,000, shooting off in space that count how many times a particular word is used in a document. So we'll have a vector has all the words in the English language, from A words all the way down to Z words, and it'll be like how many times did aardvark appear in there? How many times did calculus appear in there? Right, so it'll count. Some of these will be lots, some will be zeros, it'll be sparse, but then it'll be counting how many times, and it's easy for computers to OCR and scan this and get these vectors, these document vectors. And then when someone wants to search on vector calculus, let's say, they would come in and make a query vector that only hit on the words vector and calculus. So vector, calculus, everything else is zeros. And then it would find which of the vectors in space, there's just tens of thousands and millions, billions if you're Google, of these vectors all pointing out in space. And then there is the one you're really interested in, let's say this one, which is your query vector, and that comes in. And then the question is, which documents are closest in angle to your query vector? So you're gonna go ahead and like imagine sweeping out a cone around this red vector. We know how to make those cones now from book 3. We'll do more of those also in chapter 2. So we have a cone around the query vector, and we're finding out which of these document vectors, which might be really long, but the angles we're interested in because that tells us topical similarity, are closest. So there might be one all the way over here that didn't make it in my cone of interest, the cone around my query vector, but there might be 5 or 6 that did, and those would be returned to the user. And all of this can be done, the neat thing with linear algebra and learning how to do these dot products on sparse vectors very quickly, and some of those can be pre-computed and assembled at query time, so these things can be done very quickly. Okay, so that was dot product. One more now, I have to do the cross product. Okay. So this one's a bit more complicated again. Might take a few, doing a handful of these till you really have the method down. This time, the reason we want to take 2 vectors as input, 2 vectors, a u and a v, And now what I want to do is get a cross product. And this cross product, I'll tell you the algorithm for producing it, but what it produces, let's say that these two are more shooting like this. Those two vectors actually create a plane, right? So the plane defined by these two vectors. Well, when I cross product the blue and the black vector, I'll get this red vector, which is orthogonal to both. By definition, that was the reason the cross product was created, so that it would create this red vector, which is orthogonal to both. And that's really useful when we're talking about planes. We're going to use that very often because I want to, given two vectors in a plane, get the equation of the plane. And one way that's really easy is by getting its normal vector. That's a phrase we learned from book 3. The normal vector is the vector that describes the plane, the A, B, C components that give you AX plus BY plus CZ equal D. Those are formed by getting any two vectors in the plane and cross producting them. Okay, so how do we do a cross product? Let's take those same two vectors. Okay, and this is the page titled Cross Product, has this definition in the box here, in the gray box. And that's something, again, if you're a person that likes to make a study guide and memorize things, you can have that formula down. Or I think what's really much better and easier to remember is this visualization here of setting up a matrix. And it also helps if you're a person who's had linear algebra. This might, definitions of determinants and things might mean something to you. And so this visualization here is the way you're actually going to compute them, probably much more likely than memorizing up here. Okay, so I'm going to do that, set up a matrix for our example. So what you do is you put I, J, and K, because remember those are the standard unit vectors along the x-axis, the y-axis, the z-axis, 0, 0, 1, or sorry, 1, 0, 0, 0, 1, 0, 0, 0, 1. And then you're going to put your U in the first row, your given V in the next row. And then we're going to do this cross product operation, which actually ends up being determinants of submatrices. Again, if you had linear algebra and know those words, great. If not, just watch the visualization of what's happening here. So this is going to be equal, so this is U cross V. I'm setting up the matrix, and we're going to have 3 matrices below it. So plus, minus, plus. And I'm still going to write the I, J, and K as sort of my headings for my 3 columns. Copy my U's and V's. Okay, and then what you're going to do in the first one, notice my signs are plus, minus, plus, and that's always going to be the case, these alternating signs that you're going to use. And then you're going to imagine that you've removed the first row and first column. And what you're left with is this little 2x2 submatrix. And then you're going to compute the, well, it's really a determinant of this 2x2 submatrix, but it's also just a cross product. You're going to do 1 times 3 minus 0 times 2. And that's how I got its name, cross product, right? So 1 times 3 times 0 minus 2. So, and that is in the box, the definition of your components, right? This is really the U1, U2, U3, V1, V2, V3. So in the box on that page, this is the U2, V3 minus the V2, U3 component. And so we'll have 3 minus 0 is 3. And that is, this is also our I component. So if we're going to put that there, I, J, K. So we're going to have 3 for our I component, which is the first component in our output vector. And then we're going to do the same thing for the second one. But the second one, we're going to remove the second row and second column. And what we're left with is a 2x2 submatrix. We're going to compute its determinant, which is also just the same as doing this crossing product, which is 0 times 3 minus 0 times 1, which is 0. you'll have minus 0 times the j component. Last one on the k, I'm removing the k on the k's row and k's column. I'm left with the 2 by 2 submatrix. I'll do this cross product. 0 times 2 minus 1 is a minus 1 times k. Now again, that stands for the first component, second component, third component. Those are vectors, or it really just gives us 3, 0, minus 1. Okay, so now I want to, the next thing I want to talk about is CalcPlot3D and working a couple problems and showing the visualizations of these. So that's the mechanical vector operations. We did vector addition, vector subtraction, vector scalar multiplication. Those are all component-wise. We did vector length and normalizing a vector. And then we did our 2 types of multiplication of 2 vectors, the dot product, which gives us how similar, how much of those vectors are pointing in the same direction. And then we did the cross product, which takes 2 vectors and computes a third vector that is orthogonal to both. All of those can be done mechanically. And then we also want to say, can tools help us visualize this? So I want to work a few problems and then we'll get to the tech tools that help us visualize. So let's see. So let's work this problem. Okay, so this point, find the point that lies 3/5 of the way between these 2 points. What does this have to do with vectors? Well, let's see about visualizing this. So you can plot this in your desktop coordinate system. Make sure you can visualize these points. And there's 2 points in space, and you can think about a vector connecting them. And you always go to create the vector from the initial point to the terminal point, you actually take the terminal point minus the initial point. So if I wanted to get the vector that goes from 0, 1, 4 to this vector, I would say v is this one minus that one, which should be square root of 3. Minus 2 minus 1 is minus 3, and positive 2. 2 points with a vector between them, and then I want to go 3/5 of the way along that vector. And we'll visualize this, and then we'll talk about how we'll do it geometrically. Okay, so we got CalcPlot3D up, and just showing you some things that you can do with this. Let's turn some of this off. Okay, so you can enter points. And so it'll often have a preset one you change. I put in the point 0, 1, 4. You can change the color and the size. Maybe I want to turn that initial point to be red. The second point, square root of 3 minus 2, 6. And we keep that in black. And then the vector between them. So I entered, let me go ahead and show square root of 3, 3, 2. Minus 3. Okay. And with this initial point, 0, 1, 4, oh yeah, you can change the initial point. So like you can start it at the origin. Oops. And, or you can move it to, our initial point was 0, 1, 4. And let me make sure I've got the point right. Oh, the second point I've got to sign off. So that's square root of 3 minus 2, 6. Okay, there we go. So there is our initial point, terminal point, the vector between them in the direction from 0, 1, 4 to the terminal point. If I wanted to go the other way, I would just flip the sign of this vector, right? Be going in the other direction. And then I'd have to change my initial point to start at that terminal point, which was square root of 3. I don't think I need that slash. Square root of 3 minus 2, 6. And let's see. I feel like I got a sign wrong again. Oh, minus here. Okay. So then you see that you can change the orientation of this vector, but we wanted to go 3/4 of the way between those 2 points, and I think what they're saying is make the vector go in the other direction. So let me take a moment here and put this all back to the way it was. It was at 0, 1, 4 was our initial point, and the vector was square root of 3 minus 3, 2. Okay, now we want to go 3/5 of the way along this line. And so what do you think you would do? That's really just scalar multiplication. So we just need to take the vector that we created, multiply it by 3/5, which is just 3/5 times this vector, which is done component-wise. So that's 0.6 times square root of 3, 0.6 times a negative 3, and 0.6 times 2. Okay, so let's see if that does what we want then. So let's create the vector that is scaled, and that would be a 0.6 times this. So 0.6 times this negative 3 plus 0.6 times this 2. Yeah, and so there you go. It scales us and makes us go 3/5 of the way. Now, what point are we at? How would we create that? 1 second. Let's stop the screen share and show how we would get that point. Is we started at 0, 1, 4, and we went 3/5 of the way along this vector. Or you can also think about these, maybe it makes more sense. The uniform, and go like this along the vector square root of 3 minus 3, 2. And that would be the new point that you're at. So go ahead and do whatever that computation is, and you'll get to the point that was our terminal point of our scaled vector, the red vector in the screen share. And this is actually a nice preview to what we're going to be doing in the next section with lines. So we're almost there to be talking about it, because we really had a point and we shot a vector. And if we just extend that infinitely, we have a line. So we're almost ready to do that. Let's see. One more thing. Calc plot 3D. There's anything else I wanted to show on that? Let me just check. We did points, vectors. Yeah, I think that's it. Okay. All right, so that's it for this one. And next time, with the next video, we'll talk about lines.